All right, so we're live. So, folks, today we are going to discuss about how derivatives affect the shape of the graph. Um, so, uh, all right, so I'll tell you a small story here. How derivatives, oops, how derivatives affect the shape of a graph. All right, so the thing that I'm gonna point out here in a second. All right, so here's what it is. Let's say you have a graph of a function, and it goes something like that, and you want to tell just based on the study of the derivatives. Derivatives means first and second derivatives, tangent lines, slopes of tangent lines, things like that. How can you tell if the graph is a V shape all the way like over here, or this other shape? So see, this is kind of the picture that I drew on the screen is two shapes combined. One of them is called concave down, and it goes like this, and the other one is called concave up. So if you put these together, you get this particular graph over here. All right, so this shape, let's say this shape again. Remember, this is a frowning face, so it's called concave down, and this other shape, smiley face, is called concave up. The easy way to remember them is either like this, or just remember that when you're down, yep, you're not smiling. When you're up, when you're when your spirits are up, you are smiling. All right. Or some other people would have said in the past, back in the day when these symbols, the emojis were not available, were not popular, because this is an invention of maybe the last, I don't know, 20 years or so. Before that, people used to say that concave down doesn't hold the water. If you pour water over here, that's gonna, it's gonna go down, and concave up holds the water. So it doesn't hold water, holds water. If you pour water here, water is gonna stay in this inside this shape. All right. So that being said, essentially our job here is to distinguish when a function is increasing, when the graph is going up, and when it is decreasing, something like this, or and when it's concave down, like in this case, both these shapes are concave down, are part of some sort of a concave down behavior or concave up behavior. So our questions here is a function increasing or decreasing just by analyzing its graph, concave up or down. All right, and you might wonder, okay, so we're talking about graphing functions here. So what's the relevance of this section, given that I have such an easy way, just pull Desmos and then I can graph any function I want. I don't really have to worry about concave up, concave down, increasing, decreasing, and such. And you are correct. So this section has become a little bit old-fashioned. So this used to be the main way to graph functions back in the day. So I would say 30 years ago or so. People didn't have performance calculators. No, they did have something, but maybe older than 30 years ago. Um, so they really did, for sure, 50 years ago or more than that, for sure they did, an analysis of functions, derivatives, and they could tell, oh, here the function is like that, concave up, here it is concave down. And this approach really goes back, if you want, goes back to Newton and the old school, Newton, the French school, Cauchy, right? There's a French mathematician who had contributions to these, and then a little later down, a little closer to our days was Leibniz, a German mathematician called Leibniz, who contributed to the analysis of such graphs based on, the derivatives, the behavior of the derivatives of a function. So this is what we are going to do in this lesson. Again, in terms of importance, I doubt that you will go and you will find a class here in our college that will pound you on, find me the derivatives with the concave down and concave up behavior with the derivatives and things like that. Because again, the material here is structured around other themes, and this is not really one of the main themes. So I would say, in order of importance, this would be, I would say, 6 out of 10 in order of importance for us. But we are required to go through this material, so I am going through this material, kind of old-fashioned again, but it's something good to know. All right. So let's take a look at the increasing behavior. So let's say we have an increasing function. So the first topic here, first topic. Oops. All right, increasing and decreasing. All right, let's take a look at the graph of a function. So let's say we have a function. This would be an increasing function, right? It goes up all the way from, let me put the coordinate system here so I don't confuse anybody. So this is the y-axis, this is the x-axis, and this is an increasing function. We see that the values of this function, go up. But that's an increasing and concave down. Now, is there the increasing and concave up? Of course, most of the functions, parabolas, cubic curve and things like that. So they're usually increasing and concave up, exponentials concave up like that. So this is also increasing. But again, I'm not going to worry about convexity or the being concave. So what I'm worrying right now is about the derivative. How can the derivative tell that this function is increasing? So folks, for an increasing function, the derivative has got to be positive at every point. So it's got to point up. No matter that you go like this, like the way you went in the previous problem, or the way you go here. So the derivative, the slope of a tangent line has to be positive. So it's got to point up. That's the point with a function. So a function f, again, by a function, I mean a nice function with derivatives continuous and things like that. A function f is increasing. And it's usually a notion that goes on an interval, right? So the interval may be a finite interval or an infinite interval. It doesn't matter. On an interval, let's call it I, just to have a name for it. If, and I say, and only if its derivative is positive. Let's put 0 in the mix. So positive or 0, what 0 will do will flatten, but you can define strictly increasing, and you can kind of go into the some techie stuff there. But I'll say it's got to be positive or 0, and that's going to give an increasing behavior. So it's a function that eventually goes up. It never goes down, so I would say so. So that's not we would call this kind of function monotonous going up. All right, so basically what you want to see, folks, what you want to check, if you want to check that the function is increasing, that's your first criterion. So f increasing, it's summarized this way: f increasing, that's equivalent to saying that f prime is positive. So let's say strictly positive. It doesn't really matter. So again, whether it's strictly positive or greater than or equal to 0, you're going to arrive to about the same conclusions. But now let's say increasing, strictly increasing, and that's going to be the criterion there. So again, that means that if you wanna go up, the slope of a tangent line, folks, has to be positive. In other words, the tangent line has to be oriented going up. So that's kind of a thing that we need to make sure about here. All right, so that's one criterion, and it's very easy to check. And I'm going to give you an example next. So let's take this function f of x equals x squared. And we know the graph of this function. So the graph of this function is very easy. We've done this many, many times before. So it's this one here, y equals x squared. The derivative of this function is 2x. And this derivative is greater than 0 if x is positive, and less than 0 if x is negative. So basically, folks, what this tells me is that if x is positive, which means, let's say from here to infinity, this side of a graph, which I'm going to color with the red. So on this side here, the function you can see is increasing. So there we go, increasing behavior. Oops, I can't write. It's too high there. Sorry about that, folks. Here, increasing. All right, so it's increasing on this interval, and then I'll color with blue. I'll color this side with blue here. That is where it is decreasing. According to my formula, the derivative is less than 0, so it is decreasing, which is not so difficult to see as you come from the left again. As you come from the left, it's going down, it stops here, then it's going up. So this is the behavior on this function. That's kind of a type of model that we have in our mind. So people had when they started associating, the sign of a derivative with the behavior of your function. All right, so that's one thing that we want to point out, and with this in our bag of tools, we can move on, and we can also discuss about concave up and concave down. So concave up, we're going to come back and give examples of these, but let me just finish up with the concave up and concave down. If we have concave up here, folks, here's what happens. The derivative here is, again, you can see it's in both words. It's both positive and negative. But the thing about this derivative is, so over here, the derivatives are negative because it's, it's going down, and obviously over here, derivatives are positive. So you can't quite say about the derivative, but directly the sign of a derivative. But one thing you can say is that your derivative itself is an increasing function. So it's very sharp going down, very negative here, but then it starts growing up, still negative, but a little higher, and then still negative, but very close to 0. Over here, it passes through 0 at some place, and then there's positive and even more positive and even more positive. So the derivative, f prime, is increasing as a function, and that really makes us realize that, the criterion that we used earlier, where we said a function is increasing if its derivative is positive, well, that criterion can be applied to f prime, to this situation, and we can say, well, f prime is increasing. That means that f prime prime is positive. So if f prime prime is positive, f prime is increasing, that means concave up. So that takes us to the second criterion over here, and that criterion, oops, sorry about that, criterion, and also here f concave up is equivalent to f prime prime being positive. So remember, f prime is increasing, f prime prime has got to be positive. So that's the criterion here. And similarly, concave down means f prime prime is negative. So I'm not going to write that. But these two together, they help us go a long way towards graphing a function without a calculator. So if you're ever stranded on a deserted island and you need to graph a function without a calculator, well, you can do that by calculating the signs of a derivative. And this is what I'm going to do next. So I'm going to give you an example here, folks, of a function that's nice to graph without a calculator. And this is going to be a problem from the book. This is example 1 from the book. And that example says the following things. I'm going to change pages here. I'm going to say here, f of x equals, so this is example 1. F of x is equal, and I'm going to get the example 3x to the 4 minus 4x cubed plus, I'm just going to copy the example here, folks, it's long, 12x squared plus 5. And it says graph this function. So let's figure out the graph of this function. All right. We have to, we'll figure out where it's increasing, decreasing, concave up, everything about the function. So increasing and decreasing are, by the way, represented like that. And people represent concave up and concave down like this. So, we're going to discuss all those possible situations. And we'll start, like we said, with a study. So study the signs, the sign behavior, let's say, behavior of the derivatives. All right, so the first thing that I'm going to do here, I'm going to do f prime. F prime is equal to 12x cubed minus 12x squared minus, all right, and over here is going to be 24x. And I'm going to study the sign of this thing here. But luckily, this thing here is factoring. I can factor 12x. And I'm going to end up with x squared minus x minus 2. All right, which factors further? Again, this is not necessary for the, I mean, it is necessary, but you can solve this equation in a different way. Now, this is not necessarily the only way you can solve this equation, but so eventually you want to say if this is positive or negative, and you can analyze the graph of this one, and you can say what is positive or negative. But for the time being, again, it's useful to actually factor this as 12x times x minus 2 times x plus 1. And see where this one has zeros and where it's positive and where it's negative. And it's very easy to say. So because if a function is non-zero, it's either positive or negative. And fortunately, this function is only 0 at 3 numbers. And we can easily say what those numbers are. So basically, we're solving the equation f prime equals 0. The solutions of that, I remind everybody, the solutions of that are the critical numbers, remember? So we can easily say what they are from here because we know the factoring of that. So x has got to be 0 and 2 and negative 1. So these are the possibilities. And elsewhere, the function has constant sign between zeros, between these zeros. It doesn't change because as we learned, if a function is, so you know, the intermediate value theorem that we did last time, if a function is negative somewhere and positive somewhere, so if a function has the different types of signs, then it's going to have a zero between those points. But if we exclude the zeros, if we say, oh, the zeros are here and somewhere else, and there's no zeros between these points here, then it's impossible to change sign. So the sign would be constant between these zeros. Now, in my case, I can figure out the signs of f, the sign of f of f prime, that is. So I can figure that out by looking at a table of values. So I can put, okay, so the values that I need to put here are -1, 0, and 2. And I'm going to put positive infinity and negative infinity over here. And I'll say, you know what, f prime, if this is x, then f prime here, I'm going to put f prime in the second row. On the second row, f prime is 0 at these numbers. And elsewhere, it's got constant signs between these zeros. So, so all I have to do is to, if you want to substitute, let's say over here between -1 and negative infinity and -1, so just pick a random value and substitute that in f prime and figure out if the sign of f prime is positive or negative. And at -2, for example, I can look at the formula for f prime, which is this one here. And I can see that's 12 times -2. -2 minus 2 is -4. So that's going to be negative times negative times, and then it's -2 plus 1, which is -1 times another negative. So that's going to be 3 negatives, and that's going to give me a negative sign over here. Likewise, choose a value between -1 and 0, and you will see, so maybe you want to use a calculator, or simply notice that if the number is between -1 and 0, then this number is going to be still negative, -1. So this number over here, subtract 2, is going to be negative, but this one here is going to be positive because between -1 and 0 plus 1 is going to be a positive number. So this is going to end up being positive, and the signs will end up alternating. You can choose another value here, say for instance 1. And if you plug in 1 in the formula of f prime, you will get, well, let's see, 1 is positive, 1 minus 2 negative, 1 plus 1 positive. So this is going to be negative. And finally, over here, plug in any value you want larger than 2, and you get a positive sign. So this behavior of f prime is not, should not be surprising to anyone. The function is decreasing, the function f. Oops, let me increase this. Oops, no, I did the wrong thing. So sorry, folks, press the wrong button. So the function f here, so folks, come on. All right, so the function f here will have, according to the behavior of f prime, will be decreasing and increasing and decreasing and increasing. And you can see that at these points, -1, 0, and 2 is where f is changing its behavior. So this function will be going down and up and down and up again. And let's check with Desmos if that is the case. So I'm going to pull Desmos over here, and I'm going to say, 1 second. All right, so Desmos is on. It's not showing here. Oh, 1 second. Okay, there we go. So it's showing now, and I am going to do the following thing. I'm going to graph that function f of x exactly like we copied from the book. So it's 3x to the 4. Oops, 3x to the 4 minus 12x squared minus 4x cubed. I'm sorry, I copied the wrong thing. 4x cubed. All right, what else is there? Minus 12x squared plus 5. Okay. So you can see exactly the behavior I was telling you about, going down, going up, going down, and going up again. All right, so that is the behavior that we see over here, and it's a bit of a kind of strange behavior in a way, but that's normal for functions like this for 4-degree polynomials, as you learn from maybe discrete pre-calculus or college algebra or classes like that, where they teach about the shape of polynomial functions. All right, so we got this behavior, and we can say in conclusion, folks, and this is something that I want you to be aware how to write this properly. So you say f is increasing over the intervals, and I'm going to put here negative infinity to negative, oh, no, increasing would be -1 to 0. Sorry about that, folks. Over the intervals, and we'll have -1 to 0 here, along with union the intervals 2 to infinity. What am I looking at? I'm looking here on the number line, folks, where my intervals are written out. So this is where it's increasing. This is the increasing part, the red part. And the blue part, which I'm going to color next, is the decreasing part. So this is where I'm getting my answers from to write down here. So I'm going to write next, and decreasing over the intervals. It's going to be negative infinity to -1, and the interval 0 to. All right, so these are the answers to the problem in terms of increasing and decreasing. Now let's go further. Can we say something about concave up, concave down? Where would that be? Would that change a lot? Well, let's take the same function again. The function was so we answered again. We answered, folks. We answered the decreasing and increasing part over here. The next thing will be concave up and down. And again, I'm going to copy the function f of x equals 3x to the 4 minus 4x cubed minus 12x squared plus 5. And I know that for concave up and down, I need to look at the second derivative, f prime prime. We didn't use much of it until now, but this is a good place to use it. F prime prime is, so f prime to begin with, we just calculated earlier, was 12x cubed, minus 12x squared minus 24x. So that was f prime, and f prime prime is equal to 36 x squared minus 24x minus 24. So that's f prime prime, and f prime prime is kind of ugly numbers, large numbers, but the idea is that we can factor 12 like we did earlier. So we can factor 12, and this is going to end up being f prime prime, because eventually we're going to look at the sign of f prime prime. So if we factor 12, we're going to end up doing 3x squared minus 2x minus 2. So we want to set that equal to 0 to find out where it's 0, because then we look away from 0 and we find out where it's positive and negative. So there's got to be two solutions here. And the two solutions, folks, can be found by looking at the derivatives of that. So now this particular function was not nicely chosen. So I'm going to have to calculate the zeros with a quadratic formula. Or if you are happy, we can calculate those with decimals. In fact, maybe you should do those with decimals. So let's see, 3x squared minus 2x minus 2. We can do that with decimals. All right. So we're looking at f prime, which is 3x squared minus 2x minus 2. And you can see that it's got two zeros. It's where it intersects the number line. It's got a zero here, negative 0.549, and another one here, 1.215. Well, let's see. These two zeros are the ones that we're going to use in our case. So we can say 0.549. Okay, so over here we say, oh, well, we got x equals negative 0.549. And another one is 0. And what was that thing? Was 1.215. Okay, so it's a mistake. 1.215. All right, so we got these two, and these two, folks, are the zeros of the second derivative. So basically, folks, what we know here, and we're going to make a table like we did earlier with the first derivative. We're going to put x here. So what do we have? We have these two numbers, negative 0.549, and the other one is 1.215. And we know that f prime now, because we're looking for concave up and down, is 0 at these numbers. What's going to happen away from these numbers? Again, you can calculate, you can plug in this formula here. So say negative 1 is less than this number, so it would be someplace here. And because negative 1 is here, I can say, well, let's plug in negative 1. 3 times negative 1 squared is 3, minus 2 times negative 1 is plus 2. 5 minus 2, 3. So this is going to be positive, which we could have seen on the graph of f prime that we did with Desmos earlier. Then over here between these two, we can plug in 0 and we can see it's negative a sign, and over here positive. So f prime has this behavior. So it's positive before it hits this number here. Let me delete this stuff. All right. And then negative and then positive. So the intervals are, the corresponding intervals for positivity are this one here and this one here. So there's 2 for positivity. For negativity, I'm gonna denote that. I'm gonna color that with blue. Is this interval here? So we can answer the problem by saying that f is concave up this way and then concave down and then concave up again. So the graph of f will be will be going down and then turning around over here somewhere, and it goes down again and turns up. All right, so this is going to be the graph of f, which is the general shape that we more or less saw in the previous graph. And we can say here the answer to this problem is f is concave up over the intervals. And I denote these intervals here. So these red colored intervals, negative infinity to negative 0.549, along with the interval 1.215 comma infinity. So this is where the function is concave up, and then we say f is concave down over, and I'm going to say over the interval, and I'm going to say negative 0.549 comma or semicolon 1.215. All right, so this is the interval where f is concave down. And you can analyze, you can compare this behavior again. So I apologize, folks. These problems take a long time to finish. So that's not uncommon in this section. Folks, if you look at the graph of a function, so I'm going to graph a function again. So the function was, and I was smarter if I didn't erase that initial graph, but I did. So I'm going to have to write it again. Sorry about that. F of x equals, and the function was again, so the function was, which one? This one here. So 3x to the 4 minus 4x cubed, minus 12x squared minus 12x squared plus 5. All right, so we say plus 5. There we go. And so my function is, you can see, oops, let's zoom in here. So you can see, folks, concave up behavior, there we go, all the way to, and all the way to somewhere here, someplace. Where we actually know where exactly from this calculation here. So if we represent the point negative 0.549, let's change that to our graph, negative 0.549. So represent the point here, negative 0.549, comma, f of this number, negative 0.549. All right, so if we represent that point, that's exactly where the passage from, folks, on the graph from being concave up to concave down happens. So on the graph is, once you pass this, you get, before this blue point, it's concave up, past this blue point is going to be concave down. And again, there's going to be all the way to, and we have to plot the other point. And the other point on the graph was at 1.215. Okay, 1.215. Let's go back there and let's plot that 1.215, comma, f of 1.215. All right, so if we plot that point, okay, so where is that point at? Oh, it's over here. So you see, the function is concave down exactly between the blue and the black point. And then once it gets past the black point, it's going to be concave up again. So that is the behavior of this function. And this is the discussion that we're going to carry out today. Now, conclusion. It takes some time to finish up a discussion of concave up, concave down, decreasing and increasing for a function. So I want everybody to be aware of these things. On the test, I'm going to put some questions, but the questions will be more limited in scope. Now, I will be more precise about these questions, but let's go back to our behavior again, and let's see that that over here. So if you go back one page, this first part of the problem where we studied increasing and decreasing also tells us something interesting. It tells us that over here, right above -1 or below -1 for that matter, what's gonna happen here, we're gonna have a local minimum because the function is going down and then going up. So it stops there at that point. And likewise here at 0, there's gonna be a local maximum because of the same behavior. And likewise here at 2, there's gonna be a local minimum. So we can actually say what these points are of local minimum and maximum by studying the behavior of f. So what should happen for a point to be a local minimum? The function's got to be decreasing on the left and increasing on the right. What should happen with a point for that to be a local maximum? The function has got to be increasing to the left and then decreasing to the right. So exactly, so this is a behavior of local maximum, decreasing, increasing to the left, decreasing to the right. The other two, behavior of local minimum points. So this is, folks, this is what we do with these things. We can find out not only increasing, decreasing, but also local minimum and maximum points. So in a way, this theory is very comprehensive, and it helps us decide if we actually consider some of these points of extreme and things like that, which is very useful in practice. For example, if you want to decide if you have a model that models the price or the profit, yeah, why not? Models the profit of a company, and you can find a point of maximum, a local maximum, then that's going to be the way you target your function to achieve local maximum. So you want to target your function carefully there, and you find that point of local maximum, then you find the sweet price, where, so you want to set up a price so that the profit is maximum. Well, that will give you that will be a point of local maximum. So you want to pay attention to these type of problems again, and you can so they're applied. So in practice, you could use these to decide on maximum and minimum behavior. All right. And one more thing, and I will be done. So if you look at the second part that we did here, you will see that these points, there's some points here, the ones that we represented on the graph as well, where the function goes from being concave up to concave down. These points here, in fact, this number here is called an inflection number. So inflection, because again, the function changes from one type of behavior to the other, from concave up to concave down. Likewise here, so this is going to be called an inflection number. So these are the two inflection numbers. Now, some people identify these with the zeros of the second derivative. They're not exactly the same, but in most cases, those will be the inflection numbers. So again, inflection number is where, or inflection point is where the curve changes from going up to going down and the other way around. All right, folks, I'm going to stop recording and